All right, so we're going to finish up something that we did not finish in 4.1, which is a mixture problem. So remember, in 4.1, we're not really worried too much about sketching by hand. We'll do more of that when we finish 4.2. But what we're going to be looking at is using a graph on the calculator to solve the problem. So first thing we have to understand is what does it mean when they give you a mixture that's a certain percentage? So let's say that you had a container in front of you of 50 ounces of liquid. And I said that out of that 50 ounces, 35% of it was acid. So not all 50 ounces are acid. That'd be 100% solution. Only 35% of the 50 ounces is acid. Maybe the rest is just water. How would you figure out how many ounces of acid are there in the solution if only 35% of it is acid? Yeah?
You would do 35 over 100 and then something over 50 and then cross multiply and divide to find it.
Okay, so yeah, you absolutely could set up a proportion and do that, and that would work. That would work perfect. Can anyone think of another way that doesn't involve a proportion? Might be a little bit simpler. Yeah.
You could transfer that 35% into 0.35.
Okay, and then
times
50 by
0.35.
Exactly. If you just take 50 times 0.35, that'll tell you what 35% of 50 is. And when you set up a proportion, you end up doing exactly the same thing. So if you have 50 ounces of liquid, and I say 35% of that is actually acid, then that means 17.5 ounces out of the 50 are acid. Any question on how we figure that out? All right, so now, the other thing we need to understand is how do you find a formula for concentration? Well, concentration, like in this problem, the concentration is 35%. Concentration is a percentage. Whenever you're finding a percentage of something, what always goes in the bottom of your fraction? Yeah, the whole, right? Whatever the total is. So like if I was trying to find a percent of questions you got right, and there were 25 questions on the test, 25 would be in the bottom. Right? So you always put the total in the bottom. And then what goes in the top? Well, it's the part that you're interested in. If I'm interested in what percent of questions did you get right on the test, let's say you got 23 questions right. I would put 23 in the top, I'd put 25 in the bottom, and when I divide 23 by 25, it tells me the percent questions you got right. It's basically the concentration of questions you got right. Okay, it's a percentage. In our case, we're going to be dealing with acid. So to find the concentration of an acid, we're going to take how much acid we have, and we're going to divide that by the total amount of liquid. Okay, so that's how we find concentration. All right, so now, knowing those two things, let's try our problem. So the problem is going to be based off the solution we just worked with. It's a 50-ounce solution, and out of the 50 ounces, 35% of it is acid. But what we're going to do is we're going to take that mixture and we're going to pour 100% pure acid into the mixture we already have. So what that's going to do is it's going to make the mixture stronger. Based on how much I pour in, I would like to have a formula that tells me the new concentration. So like let's say you add 70 ounces of acid to the mixture. I want a formula that I could fill in 70, and it would automatically tell me a new percentage, a new concentration. Okay, so what we're going to do is figure out this. So we're going to find a graph of the new concentration. So the first thing we need is the amount of acid. Now, we were starting with a certain amount of acid, and we're adding a certain amount of acid. Okay, we need both of them. How do we figure out how much acid we are starting with in that mixture? Yeah. Right, and we already did that earlier. So we know we are starting with 17.5 ounces. Plus, we're going to add some acid to that. How much acid does it say we're going to pour into the mixture we already have?
X ounces.
X ounces. So whatever we had before, we are adding that much more. Now the bottom is the total. How much liquid did we start with in the mixture?
50 ounces.
We started with 50 ounces. And how much liquid did we add to that?
17.5.
X.
X. We don't know how much we add. X ounces of pure acid is added. That's the amount we're adding. And that is our new concentration. So if you add 30 ounces of acid, you would now have 47.5 ounces of acid in an 80-ounce mixture. And if you divide 47.5 by 80, that would give you the new concentration. Now, what will the concentration approach as you continue to add acid?
Infinity.
Well, what's the highest possible concentration you could ever have of a solution if it was pure?
100.
100. That's the highest concentration you can have. As I continue to add more and more acid into this mixture, will there be a point where it hits a 100% concentration? No? Why?
Because it's already been diluted.
It's already been diluted, right? You didn't start with something that was 100% pure. You can't make it 100% pure. It's like if I gave you a bucket of white paint and I put a drop of black in it, and you mix it in. Well, you keep adding white paint to it to make it more and more white, but it'll never be 100% again because that drop that wasn't white is in there, and now it's part of it. You can't take that out. So it'll never reach 100% concentration. Okay. All right, so there's our formula. Let's set up a graph. So we're going to type in 17.5 plus x divided by 50 plus x. All right, let's think about x a little bit. That's the amount of acid that we're going to add. What's the smallest amount of acid that we could add to our mixture? 0. We could choose to keep it the way it is, and we don't add anything. As far as a maximum, there is no maximum. Assuming we have access to however much acid we want, we can pour in as much as we want. So let's just say we pour in up to 200 ounces. Now, Y is the concentration. What's the lowest possible concentration that you could have in this problem? And it can't go any lower than that.
0.001.
What are we adding to our mixture? What are we pouring in?
Pure acid.
We're pouring in pure acid to this mixture. So there's only one thing that can happen to the concentration of the mixture from where it started.
So with 35%.
Right, you can't go lower than a 35% concentration because you don't have the option of pouring in water. It says you're adding acid. The only thing you can do is choose not to add anything and then it stays the same. Or if you add some, it's going to get more concentrated. Now, we didn't put times 100 on our formula. So normally concentration is between 0 and 100%. But what would that be as a decimal? 0.1 is 10%.
0.35.
So 0.35 is the lowest, and what would be the highest? 1. Yeah. So the lowest concentration is 0.35, and the highest is 1. If you want to see it as a percentage, you'd have to just put times 100 on our formula. But here's a graph of your concentration. It starts at 0.35, and the more acid you pour in, the stronger it gets. But notice it starts to level off. Once the concentration starts getting up higher, you have to add a lot of acid to make it stronger. So like if you had a concentration at 98% and you wanted to get it to like 99%, you probably have to add a lot more to just get it 1 more percent because it's already so high. Okay. Any question on the graph of the concentration? So now they want us to figure out how much acid do we have to pour in to make the mixture exactly 75%. So we want to increase the concentration by 40%, from 35 to 75. So what do you think I'm going to add to the graph that I already have to see when the concentration hits 75%? Yep.
Y equals 0.75.
Right, we're going to add a line in at y equals 0.75. Right, so we're going to mark where the concentration hits 75%. Okay, so that's where it hits it. And now, how am I going to use that graph to figure out how much acid I need to add? Yeah.
Do the second calc and then do where it traces, or where they cross.
Yeah, I'm going to figure out where they cross. Yep. So second calc, intersect. Because they only cross one time, the guess is not important. And I get 80 ounces. So in order to raise the mixture to a 75% concentration, I need to add 80 ounces of acid to my mixture. And that's a concentration problem, a mixture problem. Any question on getting the formula or graphing it and calculating a new concentration? Yes?
What equation did you put in it for the first one?
For the first one, I typed in what I have right there. Any other questions? All right, so the last thing we're going to look at is same section as yesterday, 4.2. But yesterday, these are the kind of problems that we looked at. Okay, so we wrote that down in the notes yesterday. The degree of the top was always less than or equal to the degree of the bottom. What do you think this is going to change to today?
Greater than
It's going to be a greater. Yep. So we're going to look at problems where the degree of the top is greater than the bottom. Okay, so problems we did yesterday, you could have had something like this. That would have been problem I said find the EDM for. Okay, you would have done something like that yesterday. Or something like this. The degree in the top is equal to the bottom or smaller. Today, we're going to look at a question that looks like this. The degree in the top is going to be bigger than the bottom. When the degree in the top is bigger than the bottom, you might have just seen it. But there's something new that we can find that takes the place of the horizontal asymptote. So that's one thing that's important. When the degree of the top is bigger than the degree of the bottom, you no longer have horizontal asymptotes. Horizontal asymptotes go away. They are going to be replaced with that, the EBA. Sounds kind of like something we did. We did EBM. This is EBA. End behavior asymptote. All right, so when you divide two polynomials, okay, I don't know what they're going to be specifically. I'm just saying you're going to have a polynomial in the top and you're going to have a polynomial in the bottom. So as an example, something like that. Polynomial in the top, polynomial in the bottom. When you divide two things, you get an answer, and that answer has two parts to it. What's one part of your answer when you do a division problem? We call it the quotient, and we call the other part the remainder. Okay. So when we divide, we get a quotient and a remainder. The quotient is the EBA. So the nice thing about that is we're not having to learn any new process. We're going to use long division and synthetic division just like we've done before, except now we're not going to call the answer the quotient. Well, it still is the quotient, but we're going to also give it another name, and that's called the EBA. So when you divide, you get a quotient and a remainder. The quotient is the EBA. End behavior asymptote. So to find the EBA, this does require that we remember how to do synthetic division or possibly long division. Okay, we do need to know that. So any question on that? The quotient is called the EBA. And the reason it's called EBA is because it predicts what the graph is going to look like on the ends. Right? It's kind of like EBM. It's a simpler version of your problem that should give you a clear picture of what's going to happen on the ends. So when you're talking about the ends of your function, that's like over here and over here on the sides. What the EBA is completely useless for is what's happening in the middle. No. EBA is what's happening on the ends. And sometimes when you have a function, it's kind of hard to predict what's happening on the ends here because there's a lot going on. Right? You got a trinomial that's cubic in the top. You got a linear binomial in the bottom. There's a lot there. So can we simplify that and make it easier to see what's going on the ends of the function? That's what we want to do. Okay, so let's see if we can find the quotient, the remainder, and the EBA. First of all, to find those, we need to do the division. Is this a problem we could use synthetic division for? Yes, because the denominator is x minus a number. What number would go on the outside? Just number, just 2. And what numbers would go on the inside?
2, -4, and 3. Oh, 0 and 3.
Yeah. 2, -4, 0 for the x term, and then 3. Okay. how do we start our synthetic division? What's the first thing I do?
Bring the 2 down,
Bring down the 2. Okay, and then
multiply it, the -4.
Not going to multiply with anything with -4 yet. We're going to add something with
So put
-4.
two,
Oh, wow.
So under the -4.
So put what over here?
The 2.
You multiply the 2 and the 2 together to get 4.
You multiply 2 times 2, put that number there, and then you add them up. Okay, and then you multiply again, 2 times 0 gives me, and then add them up. And then 2 times 0 gives me 0, and we add them up. Okay, so let's identify everything they want. Quotients. What's my quotient here? 2x squared. Okay, what is my remainder? 3. Now, I told you that the EBA, or the quotient gives you the EBA. The only thing that's a little different is how you write it. The EBA is always an equation, and it always starts out y equals. What's going to go on the other side for the EBA? 2x squared. Yep. So when I say the quotient is the EBA, that's true. They're the same thing. It's just a matter of how you write the answer. The quotient is just an expression. The EBA is an equation. That's an important difference. Yeah.
How did you get the quotient again?
The quotient, so when you look at your synthetic division, that's your constant, that's your linear, and that's your quadratic term. So those are the coefficients of x squared, x, and then that's my constant. And the last number, 3, is my remainder. Okay, so that's everything they wanted to know. Any question on how we found those? Okay, so now, let's talk a little bit about the difference between the EBM and the EBA. They're not the same thing. The EBM, first of all, the EBM applies to the kind of problems we're doing today, and it applies to what we learned yesterday. The EBA only applies to today. There is no such thing as an EBA in any of the problems we did yesterday. Instead of an EBA, you had a horizontal asymptote. You cannot have both. And there's a difference in how you calculate them. The EBM is easier. It's just the highest degree term in the top divided by the highest degree term in the bottom. That's pretty quick. The EBA is longer. With EBA, you have to do synthetic division or long division. Now, even though the way that you calculate each one of them is different, sometimes they could come out the same, sometimes they could come out different. In this last problem, the highest degree term in the top is 2x cubed. What's the highest degree term in the bottom? X. And if you reduce that, what's 2x cubed divided by x?
2x squared.
So in this case, the EBM and the EBA are the same. The only reason they came out the same is because of that. Both the x term and the constant term canceled out with my synthetic division. If those hadn't been zeros, then the quotient would not have been the same as the EBM. Okay? So it's a very special case when they come out the same. Okay? You'd have to get everything to be zeros, except the first term. The first term wouldn't be a zero. So usually the EBM and the EBA are different, but if everything lines up just right and you get all zeros, they could come out the same. when the degree of the numerator is less than the degree of the denominator, those are the kinds of problems we did yesterday. And we had two kinds of asymptotes. What were the two kinds of asymptotes that we studied yesterday?
Horizontal and vertical.
Horizontal, vertical, straight line asymptotes. When the degree of the numerator is bigger, what we can end up with are asymptotes that curve. So think of an asymptote we did yesterday. The graph comes down and gets real close to that dotted line. That's getting close to a linear asymptote. Now, think of something like this. Let's say you had an asymptote that was a curve, and then you had a graph that maybe did something like, maybe it comes down and it does this. So what's happening there is we've got a graph that's getting closer and closer to something that's dotted, but this time the thing that's dotted is a curve. It's not a straight line. Any question on that? So now what we're going to do is we're going to graph the EDA we just found in the last problem and see how it looks. So we're going to compare that to the original problem. So let's use a graphing calculator to verify that 2x squared is the EDA. Okay, so what I need to do is I need to type in the EDA, which I have right there. And now I need to type in the original problem, which I don't remember. So I need to go back to example 5 and get that problem. 2x cubed minus 4x squared plus 3. And then if somebody can just remember the denominator, I'll remember the rest. 2x cubed minus 4x squared plus 3. Okay, so 2x cubed minus 4x plus 3. And denominator was x minus 2?
Yep.
Yeah, okay. So if the EDA is a good fit, as we zoom out, we should see the red and the blue getting closer and closer on the ends. Not in the middle, okay, but on the ends. Let's try zoom 6. See how it looks. Okay, that's my EDA. All right, well, we can look at part of that. Let's, move that back. Okay. There we go. So when you look at that graph, at least on the left side, does it look like the red and the blue are getting closer together? Yeah, the red is the real graph. The blue is like would be dotted. That's the asymptote. Now, the thing is, if your asymptote is a parabola, then your graph in red should also be a parabola-looking kind of thing. I can't see the other side of the parabola. So where do you think the other part of this red graph is?
Outside the window.
Outside the window. I need to go up a little bit higher. Let's set our Ymax. Let's try like 35. So there's the asymptote. And now the graph in red, we'll see the left side, and hopefully, there we go. So now let's look at that. So now you can see both on the left side, the red and the blue are getting closer and closer, and on the right side, they're getting closer and closer. That's all that the EDA is going to help you predict. What things are going to look like over here, and what things are going to look like over here. And I think the red and the blue one look pretty close. in the areas that I circled. We still kind of have to figure out what's going on in this middle section. That EBA doesn't help you with that. But is there any questions why the EBA is a good fit for the areas that I circled? Is it exact? No, it's not exact. I mean, it's really close. I mean, the red and the blue one are almost right on top of each other. It's very, very close. So that's how you verify that the EBA is a good fit. You just graph it. So now let's try to graph this by hand. Okay. So when we want to graph something like this, the first thing we want to do is figure out, is this the kind of problem we did yesterday or today? At least that gives us kind of a direction where what we're looking for. Is the degree in the top less than or equal to the bottom, or is the degree in the top bigger than the bottom?
Bigger.
It's bigger. So that means it's the kind of problem we learned about today. There are no horizontal asymptotes. But there could still be vertical. Verticals exist all the time. So let's start with that. Does anybody see what would make the denominator 0? 2. So that's your vertical asymptote. So let's draw a line at 2. That is going to break my graph into 2 pieces. Okay, vertical asymptote, think of it as like cuts a piece of string. You just made two separate parts. Now what we want to do, since the degree in the top is bigger, is find the EBA. Well, we already did that. Now you'd have to do the synthetic division and then get your answer. What did we get for the EBA when we did the synthetic division?
Y equals 2x squared.
2x squared. So the easiest way to graph that, I would just make a table, pick some values for x, and then we'll just graph them. If you plug in 0 for x, what's 0 squared times 2? 0. Now notice my y-axis goes by 2's because I needed more space. If you plug in 1, what's 1 squared times 2?
2.
So 1, 2. So on my graph, it would be right there. And if you plug, we can do a couple more. If you plug in 2, what's 2 squared times 2?
8.
That's 8. So 2, 8. And what's 3 squared times 2? 18. So 3, 18. And you can reflect all those points because this one has not, it's a parabola that hasn't been shifted left or right. So the line of symmetry is the y-axis. If you don't recognize that, then try negatives, some negative numbers as well. But all these points are going to get reflected. 1, 2, 3, 1, 2, 3. Okay, so now try to draw that parabola the best you can. And remember, make it dotted because it's an asymptote. Okay, those just keep going forever. All right. Now, what we need at this point is some coordinates. Always start near your vertical asymptote and pick some points around that. What would be a good point I could check that's very close to my vertical asymptote? 1.999. I'm at negative 3,000. So put the point down as far as you can. All right. What would be another point that's near my asymptote?
3.001.
Well, we
Or
could do.
2.00.
Yeah, we can do 3 in a minute, but we should do 2.001. And I'm up at 30,000. Okay, so I'm up as high as I can go. Now, you generally do not cross EBAs, and you don't cross vertical asymptotes. So those dotted lines are going to be kind of boundaries that we're trapped in, and we can't get out of. So let's check another point to the left of our vertical. Let's check 1, and let's also check 0. So 1, negative 1, 1, negative 1. Remember, my y-axis goes by 2s. 0, I'm at negative 1.5. So actually a little bit lower. Let's check negative 2. We're at 7.25. So negative 2, 7.25 would be about right there. So now I kind of have an idea of what that's going to look like. It's going to stay very close to this. All of a sudden it's going to curve again, and then the red and the black are going to continue to get closer and closer as you go up, just like that. Now we got to check what's happening on the right. We're going to be trapped in that zone right there, because I already have a point that's inside, and you can't get outside those dotted lines. So what would be another good x value I could check? We already checked 2.0001. Yeah, 2.5 would be a good one. 2.5, I can get that one. 2.5, we're a little above 18. So 2.5, I would say right about there. We could check 3. It's a little off the graph, but I think I can still do it. 3, we're just past 20. Okay. So I have kind of an idea of what's going on there. It's going to come down, but it has to curve and go through those points, and then continue to get closer and closer. So the ends of my graph, there and there, are going to be predicted by the EDA. The middle, you kind of got to play with a little bit and plot some points near the asymptote. Right? And if we hit graph, I think my window goes up to 30, so you're actually going to see it all the way up as high as I drew it. That's pretty much what it should look like. Okay. Any question on that one? Let's try this one, and this will be our last one. And we're gonna have to finish a couple tomorrow, but we only have 1, 2, and then we're done. So it's probably gonna take like 15 minutes tomorrow. But I don't want to rush through this. So let's finish with that one. So it says find the EBA, the vertical asymptote, and make a sketch. Okay. So let's start with the EBA. The EBA is found by doing what?
Division or synthetic.
Yeah, either long division or synthetic. Could we do synthetic here?
Yeah.
Sure. Put the 3 on the outside. What would go on the inside?
1, 4.
Okay, now before we do it, I want you to just look at what's going to happen. What's the degree of the highest exponent, highest term at the top? 2. What's the degree of the bottom? 1. That's a difference of how much? It's a difference of 1. In this one, there was a difference of 2. The bigger the difference, the more complicated the asymptote. This had a difference of 2. It's going to be a more complicated asymptote than a difference of 1. Okay, so let's see what this one looks like. Down the 1. What's 3 times 1? And 4 plus 3? 7. And whoops. So add those up. What's 3 times 7? 21. I don't really care about that because it's just my remainder. This is my EBA. How would you write that? The 1 and the 7? Yeah?
X plus 7.
Exactly. Is that a parabola? Y equals x plus 7? No, it's a little simpler than a parabola. What is this? It's a linear. It's a line, but it's not horizontal. It's on a slant. Right? So this is called a slant asymptote. So it's a little simpler because it's linear again, but it's not as simple as horizontal, but not as complicated as a parabola. So that's my EBA. All right, let's sketch that. So my y-intercept here is 7. 1, 2, 3, 4, 5, 6, 7. And what's my slope? 1. So I'm going to go up 1, right 1. Okay. There's my slant asymptote. What value would make the denominator 0? 3. So I'm going to put in the vertical asymptote at 3. And what I'm going to do is this. Let's go like this. Move that down. I don't like that the slant and the vertical, I don't have any room up above. So I need to actually just add a piece of graph paper up there. Let me just get rid of, just want the graph paper. I know you can't really do that as easy, but I need more space. Okay, so now I'm just going to extend that a little bit. Because when you have a slant and a vertical, you get an X shape. And your picture usually ends up being in 2 parts of the X shape. To figure out which 2 parts, type it in on the calculator. Okay, so my numerator is x squared plus 4x minus 1. And I'm going to divide by x minus 3. Okay. What would be a good value I could check close to my asymptote?
Which?
My vertical.
2.99.
2, so just to the left, I am going to be way down. So as far down as I can go. What's a value that's just to the right?
3.001.
Okay, I'm up at 200,000. So very, very high. Now, let's just do a couple more. Let's do 1. That's a good one. 1, negative 2. Let's check 0. 0, 1/3. Let's check negative 2, negative 2, 1. And let's do like negative 4. Negative 4 just above the axis. 1, 2, 3, 4. Just above the axis. Go one more, I guess. Negative 6, negative 1. 1, 2, 3, 4, 5, 6. So hopefully you can kind of see what's happening with this blue graph. It's coming up. It's going to curve. And it's going to get closer and closer to that red one. Now in the upper right, what would be a good x value I could pick?
4.
4? Well, that's up pretty high. I'm going to do 5 because it's not up as high. 522. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, I'm going to do 6, and that's at 20. So 6, that was 20, is about right there. And 10, well, that's as far over as I can go. When I get to 10, I'm actually at about the same height, so it probably drops down like a little bit lower somewhere there. That's going to keep going that way. And this graph is going to come down. It's going to turn somewhere. And I don't have enough room to show it, but they're going to keep getting closer and closer. Okay, so we'll practice a few more of those graphs tomorrow. If we didn't have to do the mixture one, we would have had a little more time. Okay. So we got the 48 A and B. And then on 235, let me just double check that. We're going to hold off on 51 and 55. So it's just that. So six questions. Okay, tomorrow we'll finish that up, and then we'll have time to review.